Thank you, Professor Kim. That was really enlightening talk. So I'm going to go ahead and now switch the contaminant, all the contaminants Professor Kim talked about. He did not allude to PFAS, probably, I don't know, intentionally or non-intentionally. But let's talk about PFAS now and the work that's going on with the center. So this talk is more about overview of what we are doing as a center to remove PFAS from water, and we are basically going to divide that in two main themes. One is a separation, just removal, and the second theme being the destruction. So hopefully it does justice to all the wonderful work that goes on with a lot of researchers at the center. So I want to give a huge shout out to the Emerging Contaminant Group. I'm going to name all these researchers who are leading different parts of this work. So a lot of you know PFAS, what PFAS are, these forever chemicals. Probably everyone has heard about forever chemicals, right? These have been synthetic chemicals. I think Chris mentioned that in the opening remarks. Man-made 80 years ago, nearly found in almost all the applications, right? It's present in this room as well, on the chairs, carpets, you name it, in the furniture. They are distinguished by the carbon-fluorine bond, which is a very stable bond, as you are aware. It gives them some desirable properties. That's why industries love it, and that's why even people use it in the household items. But because of that stable carbon-fluorine bond, it presents a challenge that it's very difficult to get rid of these contaminants. Well, why to get rid of these contaminants? Because they are persistent, because of that carbon-fluorine bond. Again, bioaccumulative. Many of them are bioaccumulative, not all, and not all of them are toxic, but a lot of them are toxic. And so there is a concern for human health and the environment, and if we want to look at their health impacts, and again, not all PFAS are same, right? We are talking about the class of contaminants, about 14,000 or 15,000 by US EPA definition. If you go with European OECD definition, we are looking at millions of compounds, right? So with these compounds, a lot of them have proven to be causing health impacts, a lot of adverse health impacts. These affect all the major organs, many of the major organs in the body. Some of them are cancer-causing, carcinogenic compounds. And a lot of these things also affect the immune system and fetal growth, right? So these are some serious concerns about this chemical. Why should we worry about these contaminants? It seems like drinking water is one of the three major sources of exposure to PFAS for us every day. And about more than 1/3 of the US population, about 140 million people, are exposed to these contaminants on a daily basis because they are drinking the water containing PFAS higher than or close to the limits of that US EPA advises what limits are probably safe, or the MCL levels, proposed MCL levels. And there are some fancy technologies, of course, reverse osmosis, ion exchange, and GAC. But as you will see, all of these are expensive. They are not sustainable and certainly not green. Many of these technologies are. So this is a map, a very recent map from March this year. And this just shows the places where they have done the testing and the PFAS concentrations have come above the US EPA limit. And those are the light blue circles, and the dark blue circles are the ones where PFAS were detected below the EPA proposed limits. So it's very difficult to see any visible spot in the Northeast and certainly on Long Island. So again, shows that a lot of PFAS being present in our waters. And it's not surprising when you look at why this is a concern, because the levels that we really want to achieve are pretty low. It's parts per trillion, right? So these were the proposed EPA limits on 6 of the PFAS. You will see that those all are in parts per trillion. And just for general audience, parts per trillion is 1 drop in 20 swimming pool, right? Olympic-sized swimming pools. So again, very low concentrations. So let's see what center is doing. So I think many of you were aware of this background information, and I think the purpose of this talk is just to showcase what we are doing at the levels where we feel like some of these solutions can be applied, hopefully, at the community level. So let's look at the most prevalent technology for removal of PFAS, including in Suffolk County. Many of the large-scale water utilities rely on activated carbon. I think many of you are aware, activated carbons, these are the large vessels filled with activated carbon, and these are the ones which remove PFAS, at least the long-chain PFAS. The way it works is that carbon doesn't like water, and so the things that in the water that do not like water like to stick on the carbon, right? So the long-chain PFAS are very hydrophobic, and that's why they would get attracted to the carbon, they get removed very well. But the short-chain PFAS and some of the mobile contaminants in water, they don't like to be sitting on the carbon, so they remain in the water. So activated carbon is really not a good solution if you want to remove large amounts of PFAS from different classes and from different structures. Right? It works really well for legacy PFAS, PFOA, and PFOS, but not necessarily for other PFAS. But it has other problems too, because it attracts everything that doesn't like water. It also attracts organic matter. And because it attracts the organic matter occupies the space on the activated carbon, preventing the PFAS from coming in and absorbing on the carbon. And because of that, we call that as a GAC fouling, which means that the GAC gets fouled by the organic matter, and you have now no more removal performance, even for long-chain PFAS, right? So all those vessels, they become pretty useless after a certain time because they get fouled. When you look at why this is a concern, so activated carbon itself comes from, it's not local, it comes from very different places. If you have a coconut shell-based activated carbon, it comes from tropical country, right, the coconut shells. If it's a coal-based, certainly not a green technology. But those are the two major sources of activated carbon. And if you look at the cost for its replacement, so that vessel shown in the picture, it takes about $90,000 for replacement of the media for one vessel. And there are 200 vessels in Suffolk County, more than 200 of those. So you can imagine $18 million per every change of the activated carbon in these vessels. So that's a very large amount. So it's very understandable when we saw the recently released PFAS treatment budget from Suffolk County Water Authority. It's $50 million, and you will see that some of these similar numbers around the country. So what are we doing about this? So the first and foremost, to tackle this GAC fouling, our research led by research scientist Dr. Philip Wang has been looking at trying to understand the mechanism of fouling better. He has extensive experience in looking at adsorption processes, but more importantly, adsorption in the presence of dissolved organic matter. And these are the very simple experiments, right? But it takes a lot of time, a lot of meticulous design. And what we are seeing consistently over different pH is that we have water that are near circumneutral pH, around pH 7, would actually have a lower impact of dissolved organic matter over the PFAS absorption. So the black dots are the ones without the dissolved organic matter, and the blue dots are the one with dissolved organic matter. So the lower the difference between the black dots and the blue dots, that's the better. So as you will see, pH 5, 6, 7, at pH 7, the gap reduces significantly. So simple advice, but this advice to the utilities could be very useful because we are aware at least a couple of treatment plants in Nassau County, their GAC treatment is at an acidic pH. So just by simply raising the pH towards 7 potentially can have an impact on the PFAS absorption. They can probably see more PFAS absorption and lasting GAC lifetime. We don't just look at its removals, we try to get deeper into the mechanism and why this is happening. So anyone who has worked with dissolved organic matter would probably realize that dissolved organic matter is really complicated compound, right? It's not a simple chemical structure, USIN C6H12O6, it's not a glucose, right? There's no chemical formula, it's a very humongous molecule. And so when you look at the dissolved organic matter structure, what we believe what's happening at pH 5, which makes it a lot more competing with PFAS for adsorption, is that the dissolved organic molecule gets a lot more compact because of the hydrogen bonding. So the pH 5 molecule, the same DOM molecule at pH 5 and pH 7 is shown there, which means that at pH 7, if you can basically have a DOM which is not having this compact structure, then probably it's not going to compete with PFAS. And that's why you will see a lot less fouling and probably better removal of PFAS. Again, a simple advice, but going into the mechanism, we basically get to understand how we can advise the utilities in terms of what may improve the PFAS removal performance. And again, that 10 or 20% gain that we obtain by changing these conditions, you can translate that to the millions of dollars saved based on all those figures I showed earlier. We are seeing this consistently across the different structures of the DOM, the fulvic acid and humic acid, two major components of humus. And we are seeing that for many different PFAS, as you can see, and also for these two different pH tested, pH 5 and 7. pH 7 consistently is a better pH to run the water when it comes to the PFAS option. What you are seeing on the y-axis is basically you can think about the suppression effect, right? If it's close to 0, nothing like that. That means that's what you want. You means the DOM suppression of the PFAS absorption is less. And what you are seeing in these figures is that consistently both fulvic acid and humic acid, the blue bars are lower than the black bars, which means that, again, at pH 7, you are getting less suppression. So this what we establish is that throughout, for all the PFAS, having the pH around 7 is beneficial compared to pH 5 to get a better removal of PFAS. Well, the next project I'm going to talk about, we are really, really excited about this project. What we are looking at is the earlier slide showed you how we are trying to work with the current adsorbent, GAC, and how we are thinking about using some of this mechanistic understanding to improve its lifetime. Now we are thinking about what if we change the GAC and we use the adsorbent from the natural resources, right? And Long Island is blessed with a lot of natural resources. Being a coastal area, we have a lot of kelp. We have a lot of oyster shells, for example. What if we convert this into adsorbent and use that instead of GAC? But more interestingly, the bamboo, right? I think a lot of people are from Suffolk County. You must have seen this bamboo forest, as we call those, a lot of places. And bamboo is not a native species. It's an invasive species. The way a town of Brookhaven deals with bamboos is basically they cut it down and they put it in the landfill. So we thought, what if we take this waste, natural waste, and use it to convert that to an adsorbent that can replace the GAC? And so that's why we are excited, because we can use these natural resources to look for alternate media for the GAC. So how this process works is basically a pyrolysis process is where you have the feedstock, these different feedstocks I mentioned, kelp, bamboo, oyster shells. You put that in the pyrolysis plant, and it produces three products, the solid, liquid, and gas. The solid is the one that's called the biochar, and that's what we are interested in. We can optimize the condition to maximize its yield, and that's the one we use for water purification. So, and again, this is Suffolk County Water Authority is here, and I want to really thank them because this concept, with some preliminary testing, we got their first inaugural innovation in a water treatment grant, a water research grant. And that grant was for the same purpose, for converting some of these feedstocks into the biochar. And on the right, you will see the results, preliminary results for the kelp biochar. Again, if you look at it, if you just look at in terms of same weight basis, it may appear that kelp biochar is having a lower performance in terms of removal. And this is, again, just one-step optimization. We are in a very primitive stage of this research. But even with that cost saving that we are getting with the kelp biochar compared to the GAC, on all other matrices, this turns out to be a superior adsorbent compared to GAC. So if you do the complete life cycle analysis, it would come out to be a superior adsorbent compared to GAC. What we are excited is that we already are on the path to make this into a big project, and we are naming it as a Charlie, Char for Long Island's environment. We have currently those two stages. We have the bench scale furnace. We recently acquired the pilot scale furnace, and it's a very, very humongous furnace. We are just trying to find the space for it currently. But our goal within a couple of years to actually move to the full commercial scale with these biochar applications where we can actually convert all this organic waste into useful adsorbent. And a lot of people are involved here. Of course, Chris is there, myself, Dr. Ben Shaw from Swift Labs, and he's also a distinguished professor here. Dr. Philip Wang, as I mentioned, Dr. Young Kim, Anna, who is a PhD student, and Walter, who is also leading this project. I'm excited about this innovation that we are doing, keeping the theme of the alternate adsorbent. We are working with Swift Labs and Dr. Ben Shaw to come up with another alternate material which we believe actually takes out some of these disadvantages of GAC with clogging and with fouling and so on. So I'm just going to press this and see if the video works. Hopefully it does with the audio.
This is a hydrosponge. We can make it in any size or shape. It's primarily made of cellulose, with a few added functionalities. We harvest this cellulose from plant waste using the patented nitrooxidation process. NOP is a simple, zero-chemical waste treatment which upcycles wastes into fertilizers and cellulosic technologies, one of which is carboxylated nanocellulose, which we believe can help assist in water purification in local communities around the world, and especially here on Long Island. PFAS in drinking water is an important concern. Commercial granulated activated carbon, the current standard for PFAS removal, is unable to trap short-chain PFAS. GAC cartridges also require the use of secondary particle filters. We propose a low-pressure, porous sponge polishing filter, capable of shape recovery that resists clogging and channeling. Preliminary results indicate that our cellulose hydrogels are capable of absorbing long and short-chain PFAS. We envision this technology as a PFAS polishing cartridge that can be integrated into existing water filtration systems.
So as you can see, we are pretty excited about this. Those are the real products that you saw, and I'm glad to report that we were the 4 winners out of 670 applications for the Brook and Beyond Innovation Challenge. So we just recently received that news a couple of weeks ago. Thank you. The way it works, it's pretty straightforward. So all this funding is to make it now commercial, so that's what we are working on, to make it a large scale with the help of Dr. Benshaw and Swift Labs. The way it works is in the cartridge, you put these sponges on, and with the hydraulic press, if you press it, the pure water comes out, and it then releases and is ready to intake the contaminated PFAS water, right? PFAS contaminated water. It stays there for a certain time, where the PFAS adsorb onto the nanocellulose, and then again, the sequence continues where you press it, and you get the fresh water back. The main advantage being, again, less fouling, a really good flow, and what we believe is very cheaper cost and very green technology, because we are using the organic material to convert that to the adsorbent. So this is our plan going ahead. What we are planning to do, the 2 technologies we showed, the pyrolysis and nitrooxidation process that you saw for those nanocellulose filter, we want to create waste to value center of excellence. Where? And this is what we pitched even to Lee Zeldin last week when he was here, and at least on the face, he was supportive of it. What we are finding is that if we take these materials, it's not going to only produce the adsorbent for water treatment, but it can actually have different applications. It can have an application for a biochar for soil, for example, for agricultural purpose, where you potentially can get more crop yield by trapping these nutrients in the biochar. It also can have application in the construction industry, for example. So even though our center is focused on water treatment, we believe that this multifaceted approach would actually make it a lot more attractive for people and industry to move towards this adsorbent to waste to value approach in terms of adsorbents. So I'm going to give overview of a couple of other treatments that's going on at the center when it comes to the removal of the PFAS. And we are working, again, with materials, not as fancy as Dr. Kim's, but the materials which we can potentially see large-scale application in the field. So something like very simple aluminum electrodes. So what we are doing in this research is just passing the current in the aluminum electrodes. We are trying to get aluminum hydroxide, which is a precipitate, and that precipitate would trap the PFAS as a sludge, and then the bubbles that get produced at anode and cathode by breaking of the water into hydrogen and oxygen, those would also trap some of the PFAS and rise that PFAS on the top. As any of you who has worked with PFAS know that they behave like surfactants, right? They are surface active, which means that they can actually get trapped in the bubbles and float on the surface. So you can remove the sludge, and you can remove the bubbles on the top, and you can get removal of the PFAS in this unit. So that's a simple concept, just passing the current into the electrodes, which are easy to get, easy to scale up. We are seeing really good removal of PFAS. You can see that about 99% and 97% removal for PFNA and PFOS, about 75 to 80% removal for PFOA. We just recently optimized this PFOA removal, and it's now going above 80% with really good increasing the stability of the bubbles. And we're getting about 70% removal of PFH excess. So again, really good when it comes to the removal of the long chain PFAS along with PFH excess. And we do not just do the removal, we try to understand the mechanisms, right? So we try to see where these PFAS are partitioning in these phases, whether they are remaining in the water, whether they are going into the bubbles, or where they are settling down in the sludge. And when we do this phase distribution, we can clearly see that the long-chain PFAS, even the PFAS and PFOA behave differently slightly. PFAS, you can see a lot more get trapped in the sludge. The purple one is the flotation. It goes on the top. And the bubble, and very small, 3% only remains in the water, the green one, right? So the small remaining in the water is what you desire, right? For PFOA, about 30% remains, and again, as I said, we have optimized it now, so it's still about 19 to 20% rather than 29. But what we get is more distribution, equal distribution in electroflotation and precipitation. And unfortunately, the short chain ones and Gen X don't get removed. So we are working on trying to understand how we can improve their efficiency. But this is, again, done at a continuous flow and with the aluminum electrodes. So again, very close to the real-world applications. I showed that the short chain don't get removed with electrocoagulation. We are working on it. But Dr. Yi Zhang, who is a research scientist here, she saw this problem with the short chain PFAS with different treatments. And she said, like, what if we tackle that problem heads on? And she developed this material along with Dr. Ching here, who is our center's collaborator, to see if we can actually target C4, the short chain PFAS that escape this electrocoagulation and some of the other techniques. And what they're working on is molecularly imprinted polymers, or in short, what we call it as MIPS. And the concept is very simple. You basically make a cast sort of with the target PFAS that you want to capture. Right? And you create a hole of the same size, right? This is in a simple terminology. And then take that hole and try to put it in the water, and that hole hopefully will not take anything else except the target PFAS you are targeting, right? And so if we did, and this is again at a preliminary stage, the work, but then what we are seeing is a very good removal of short chain PFAS. And you rarely see that short chain PFAS removal exceeding the long chain, but with this MIPS, we can see that clearly C4s like PFB and PFBS are getting trapped better than PFOA and PFOS. So I'm going to move to the destruction part. So this is all good when it comes to the separation and sequestration of the PFAS, but as a conscious citizen, really, I want to see is that PFAS get completely destroyed, right? If we can convert that to the harmless fluoride, that would be the goal. And we have been working with different technologies for PFAS removal. Staying with Dr. Yi Zhang's research, she has been doing this work with, again, Dr. Ching for about 3-4 years, last 3-4 years, looking at vacuum UV treatment for PFAS. And I'm glad to report that yesterday was the first test of a very large, about 5 gallons per day to 10 gallons per day continuous flow operation, which was very successful in terms of removal of PFAS. And so you can see the two devices. The vacuum UV has been shown to be working very effectively for PFAS removal. The problem with vacuum UV is that it's a very high energy and high intensity UV light, which means that you are spending a lot of money in actually giving the treatment of PFAS. But what we have come up with this novel device is that do the same treatment with the same efficiency at much lower cost. And that's where the patent has been filed, and I believe it's provisionally approved. And that novel plug flow UV system is the one where we are now doing the continuous flow testing to see the performance for different PFAS and real-world mixtures. And we hopefully would be piloting that with the Suffolk County Water Authority in the near future. So these are just the results for PFAS, and AGW refers to artificial groundwater and milky water. As you can see, even having some of the constituents in the groundwater, it does not seem to have impact on its performance. So with this device, we are getting across the board good removal of PFAS except PFBS without any additive. So this treatment works without having any additives. Again, emphasis being on the green treatment. And when it comes to the cost, again, as I mentioned, the vacuum UV has been studied by other researchers, so what's the new thing? With this device configuration, as you will see on the right side table, the values by which we measure the cost for the treatment of PFAS, which is defined as electric energy per order removal of the PFAS, that cost is significantly on the lower side compared to the current existing treatment technologies, right? So if you look at those on the right side graph on the top right, you will see the calculated EEO values for some of the commonly used treatments. And on the table below it is what we have EEO values for the vacuum UV, the novel reactor that you saw on the previous slide. And these values, again, being in tens and 20s as opposed to hundreds or thousands in some of these other treatments. Next, I'm going to go again to Dr. Sheng Yin, who is a postdoctoral researcher who also did the electrocoagulation work. He's also actively looking to see, well, it's one thing to separate the PFAS. What would we do with this concentrated PFAS in, say, for example, foam? He's looking at the way to destroy this PFAS, again, with the same concept. And again, with the very simple electrodes, not any fancy electrodes. So this work was done with the ion electrodes, where he's using the ion electrodes to look at the PFAS destruction, particularly PFOA destruction, and what we are finding is that we are able to get about 90% removal of PFOA, not just removal, it's conversion to the fluoride. So again, without going too much in detail what with the mechanism or any of those differentiates mean, what you want to see is on the top left side, the figure. The red one is the PFOA concentration tested in the reactor, and the green one is the defluorination, which means that PFAS getting converted to the fluoride. So this is what you want, the complete destruction of the PFAS into the fluoride. And you will see that we actually are able to get about more than 90% removal of PFOA with this lab synthesized iron oxide. And again, not a fancy electrode, just again stressing that it's simple ion electrodes. By understanding the mechanism better, by understanding which conditions would actually remove PFAS, we are able to optimize this reactor. Not only we remove the PFAS, but true to being green, we actually want to recover the ion that's used in this, on this electrode. So the ion dissolves and actually goes through the redox cycle, Fe3 and Fe2, as some of you probably are aware how ion behaves. But we recover that ion from anode to cathode, and we get the recovery of about 85% of the ion. So not only, again, we are removing the PFAS, we are conserving the material by recovering the ion on the electrode. And what we are finding, again, for this condition, though, the pH that actually works better is slightly acidic. So again, these informations, again, help the utilities to see where this treatment can fit and what kind of water conditions you need for removal of the PFAS. We are not only working with utilities, public partners, which is great. We want to do that for practical applications, but we want to understand the fundamental mechanisms. And we have a lot of good collaborators, academic collaborators, that work with us on different mechanisms. So for this work, we actually collaborated with the Rice University group, which did the computational chemistry calculations for us to prove how this PFOA oxidation is happening. So you can see the cycle, again, without going too much in depth, we can see all these intermediates forming in our reactor, proving the mechanism, and having a good handle of mechanism means we can optimize the conditions. Finally, what we are really excited, we recently received the news last month that we were awarded as a subcontractor, the award from DOE for the plasma treatment. So we are going to look at this thermal plasma treatment in combination with vacuum UV and electrochemical oxidation that we are doing to see the complete destruction of the PFAS. And the reactor we are currently working on it's shown in the right side, conceptual reactor with our partners, the sponsors of the project, is the one what we want to see being operational 6 months from now. It's again going to be a continuous flow reactor resembling more real world conditions, and we are going to pass the real groundwater through it. So the results that you see is in that crude reactor, but hopefully that's the metamorphosis you will see in the next symposium, where we'll show you the cool design of our thermal plasma. All right, with that, I would like to conclude my talk, but again, all of this would not be possible without wonderful members of my group. They have been Dr. Philip Wong, Dr. Sheng Yin, Mahima, Dr. Yi Zhang, Anna, Dr. Young Kim, Dr. Rahul Kumar, Kevin Schaffer, and we have some wonderful collaborators, Dr. Ben Shah, Dr. Qingzi Zhu, and Dr. Qingwin Li, and all of them have been really amazing to work with last 2 years. So I want to give a huge shout out to them and our sponsors. So thank you, everyone.